Okay, good afternoon, everybody, and welcome to the Computational Science Colloquium series. Today we have the pleasure to welcome Professor Junfei Xie from the Electrical and Computer Engineering at San Diego State University, and she's going to give a talk about network for airborne computing in uncertain space. Professor.
Thank you for the introduction, Dr. Jose. So today, I would like to share with you some of my recent research results. The topic is about how we can enable networked airborne computing in uncertain airspace. This is the outline of today's presentation. So first, I would give you a brief introduction, and then I will introduce some techniques that we have developed to enable networked airborne computing, and then we'll briefly talk about some applications enabled by networked airborne computing, and then end with future work. Unmanned aerial vehicles, or we call drones, have become quite common in our daily lives, and will make more impacts in the near future. So, for example, we are familiar with the many drone applications, such as we are familiar with the scenario that we see a tourist that using the drones to take pictures from with area view, and we also familiar with the scenarios that we probably have seen some drone light shows through YouTube or probably in some social events. So in addition to these applications that we are familiar with, the drones have been widely used in many other civilian or commercial applications, such as the examples shown in these pictures. For example, we can use drones in agriculture to spray the crops. We can use drones in emergency scenarios like firefighting. We can use drones to deliver packets. We can use drones to search and rescue. And we can also use drones for geospatial surveying, and even use drones to transport people, passengers. So with the growing, popularity of these drone applications, and also the growing needs for computing resources to realize such complicated, advanced UAV-based applications, networked airborne computing has recently attracted increasing attention from researchers. The networked airborne computing refers to computing in the airborne area layer through the airborne network, where the airborne network consists of multiple UAVs that directly communicate with each other through flight-to-flight communication links. Currently many companies such as Google, Facebook, Amazon, and Nokia have launched projects to explore applications that use UAVs with computing capabilities. So why we need networked airborne computing, and what are their benefits? So next, let me answer these questions first before we introduce the enabling techniques. To realize a UAV application, it is necessary to design and implement multiple UAV functions. Take the drone light show as an example. To enable this application, we need a path planning function to plan the path for the UAV. And we also need a positioning function to determine the accurate position of the UAV. And we also need a flight control function to control the UAV so that it can follow the trajectory and can land safely. And we also need power management, communications, and networking functions for coordination and management purposes. So certainly, many advanced UAV functions require a high performance onboard airborne computing capabilities. So how we can however, existing UAV platforms have limited computing capability. So how we can address these limitations so that we can enable high performance onboard computing to support these advanced UAV functions. So the solution is using the network airborne computing. The idea of it is to let multiple UAVs to share resources among each other. So in addition to enhancing UAV functions, networked airborne computing have many other benefits. Right? It can not only benefit a wide range of existing UAV applications by allowing UAVs to implement advanced functions. It also can give rise to a variety of new applications. For example, UAVs can be used to facilitate data collection, processing, and distribution for IoT devices or in wireless networks. And we can also use UAVs to function as a computing server to provide computing services to ground users. We can also use UAVs, for example, to implement some advanced algorithms to advanced antenna heading control algorithms to improve the communication capacity for the communication link between two UAVs, if the UAV are equipped with directional antennas. So next, let me introduce some of our recent efforts to enable networked airborne computing. So first, I will talk about our design for a hardware platform to facilitate research on networked airborne computing. So the design of UAV platforms has largely ignored the computation aspect. Most existing studies on the design of UAV platforms mainly focus on the control, communication, and the networking aspects. So most existing UAV platforms have very limited computing capability. To execute computational intensive tasks, existing solution is to offload these tasks to the ground. However, as the communication bandwidth between the ground and the UAV are very limited, such computing model can cause a lot of issues. For example, it may lead to significant transmission delays or even failures. For high bandwidth applications, such as transmitting a video, such a computing model requires large communication bandwidth, which may not be feasible. So to address these limitations, we propose a networked airborne computing platform that incorporates all necessary functionalities to enable networked airborne computing. In particular, it consists of 4 core units. The Quadcopter unit is used for lifting and mobility purpose. And the control unit is for the control of the mobility for the UAV, as well as control for the directional antenna, where the directional antenna is used for communication between two UAVs. The communication and the networking unit is to achieve long-range broadband communication, and the computing unit is used for onboard processing and storage. So next, let's look at each of these 4 units in more detail. So first, the Quadcopter unit serves as the platform carrier. Compared with fixed-wing UAVs, quadcopters are easier to operate and can hover in the air and can achieve vertical taking off and landing. So because of these nice features, we choose quadcopter as the platform carrier. So of course, the quadcopter has its limitations, such as short flight time. And these are some drawbacks that we need to address in the future. And now let's look at the control unit. This unit consists of 3 subunits. First is the autopilot control subunit. This unit allows an individual UAV to maintain stability and to follow certain trajectories based on the information from the onboard sensors. The antenna control subunit supports the control of directional antennas or phase array for directional networking. The reason why we use directional antenna instead of omnidirectional antenna is because, as we can see in the right picture here, the directional antenna, by focusing signals along one direction, it expands the communication range between two UAVs and achieves broadband communication. The third subunit is the cooperative mobility control subunit, which addresses the networking and the cooperative UAV application needs. So one place I forgot to mention is, as we choose the directional antenna, one key thing we need to address is, in order to achieve robust communication between two UAV with directional antenna, we need some control algorithms to control the direction of the antenna so that they can keep aligned to enable robust communication. As the right animation shows, the direction of the two antennas on the two UAVs needs to point to each other to enable long distance and robust communication. The third unit is the communication and networking unit, and this unit achieves two types of communications. One is air-to-ground or ground-to-air communications, and this is achieved using a commercial off-the-shelf Wi-Fi access point. And another type of communication is air-to-air communication, and we use a directional antenna with a Wi-Fi router to achieve this communication. And as the picture shown at the bottom, the UAV, we have the ground servers that can communicate with the UAV through Wi-Fi access point, and we have two UAVs to directly talk to each other. And the computing unit offers computing and storage capabilities and supports other units. To allow a flexible and adaptable or a platform that can be easily configured and that allows users to easily design their own applications, we designed this system architecture, which consists of 3 layers, together with the platform API and also the hosted applications and virtual network functions. The 3 layers include, at the very bottom, we have the hosting infrastructure layer, which contains all hardware resources such as CPU, GPU, drone, directional antenna, sensors, and so on. In the middle, we have the virtualization infrastructure layer, which provides support to virtualize physical resources. And about why we need virtualization, I will talk about this more in the future slide. Oh, okay. Seems that the last somehow with some issues with the slide. So in the very top, we have the application layer, which supports the development for the applications and the network virtual network functions. As the UAVs operate, as the computing unit is placed on the UAV that operates in an uncertain national airspace system, there are some unique features we need to consider when we select suitable single board computers as the computing hardware. So first is the single board computer should be lightweight and have a compact size, considering that the UAV has very limited payload. Also, it should have an efficient power management system to reduce power consumption, because for quad rotors, which usually use batteries to power the system, and batteries have very limited power capacity. So efficient power management system is also required. And of course, we also need power for CPU to sufficient memory and storage to support most of the computing needs. And a power for GPU is also necessary to enable real-time image processing and deep learning capabilities. And besides of all these aspects, we also hope that the computer hardware can have extensive community support so that developers and users can communicate with each other, so in case there are some problems. And last but not least, we also hope to have sufficient open source design documentation and configuration toolbox. So in order to select a suitable single board computers, so we did a comparison of state-of-art single board computers. So for existing UAV platforms, the single board computers that are commonly used, such as Raspberry Pi and Arduino, have very limited computing resources. So we are not consider them here. So instead we find 10 state-of-art single board computers and compare them from different aspects, such as CPU, GPU, memory, connectivity, dimension, power consumption, operating system weight, virtualization support, storage, and price. And through the comparison, we finally pick JSON TX2 as our computing hardware, so which has power for CPU and power for GPU, memory, and some other nice features. And of course, very recently, there are some more advanced single board computer that are developed by NVIDIA, but we haven't considered that into this study. This study was performed last year. And here is a prototype that we developed. So as we see here in this picture, the white parts are the hardware that we developed, which can plug in and plug out, and can easily put in any UAV platforms. And at the very top are the antennas, directional antenna, as well as some other components like campers, and motors, GPU, or Wi-Fi router. So as you see here, the direction antenna is placed on the tuning plate, which is driven by a motor, so that we can turn the direction antenna towards any direction we want. So in this way, we can, by designing some heading control algorithms, we can make the directional antennas at the two UAVs to point towards each other, even when the UAVs are moving in the air. And at the bottom, highlighted by this yellow dashed curves, are the computing unit together with a carrier board. So the original JSON TX2 has a very big carrier board, which is heavy and big, which cannot be carried by the drone. So we developed our own carrier board, which is lightweight and small in size. And this carrier board is shown in these right two pictures. And this carrier board includes all the ports, various of ports to support all the needs. Okay, so now we have seen the hardware design to enable networked airborne computing. Next, let me introduce some software and algorithm design to enable network airborne computing. To improve the flexibility and the programmability of the airborne computing platform, virtualization is needed. Where virtualization refers to the process of creating virtual representations of physical hardware to allow multiple operating systems to coexist. Virtualization has many benefits. For example, it can provide powerful resource management capability. It can also enhance the security by isolating unreliable and untrustworthy functionalities. And virtualization also supports concurrent execution of applications, even if they have different operation system requirements. And virtualization can also help to exploit the distributed computing capabilities on multiple connected UAVs. Although virtualization has been widely studied in the literature, virtualization for UAV has been rarely studied. So we investigated 2 representative virtualization techniques and see what is its impact on the UAV platform and how it can support UAV applications. The first virtualization technique is called kernel-based virtual machine, which is a representative of the hypervisor-based virtualization techniques. And this technique performs virtualization directly at the top of the hardware resources, hardware level, by using hypervisor, where the hypervisor abstracts hardware resources and creates simulated operating environments called the virtual machines. The virtual machines access the physical resources through this hypervisor. And this hypervisor-based techniques require hardware virtualization support to achieve CPU or memory virtualization. And these techniques will enable full virtualization of the hardware resources and therefore provide good isolation and security. The disadvantage is that because it requires full virtualization of the physical resources, it generates high performance overhead and it can misuse resources and is slow in startup process. The Docker is another virtualization technique. It's a representative of the container-based virtualization techniques. Unlike the hypervisor-based virtualization techniques, Docker provides very lightweight virtual mechanism, and it abstracts at the operating system level. And the virtual environments are called containers. These containers will share kernel with the host operating system, and this technique does not require hardware virtualization support. The advantage of these techniques is it generates low performance overhead, and it can be quickly deployed and are portable across machines and is simple and can be quickly configured. But the disadvantage is it is less secure because it shares kernel with the host operating system. So we did a comprehensive comparison between these 2 techniques on Jetson TX2. And our conclusion is that the Docker overperforms KVM in most aspects, including CPU and GPU computing performance, networking performance, as well as isolating as well as the performance in isolating most hardware resources, including CPU, memory, disk I/O, and the network. And it also consumes less power than KVM and is more lightweight. But the advantage of KVM is more secure than Docker and is more resilient to virus attacks. So in the future, we aim to, we propose that these 2 techniques are better to be integrated to provide a better virtualization solution. The next part that we explored is distributed computing. As the computing capability of a single UAV is very limited, it's still limited, even if we equip the UAV with high performance computing device, computing hardware. So how we can further enhance the computing capability of UAV? This can be achieved by using distributed computing techniques that allows resources to be shared among multiple UAV so that a resource constrained UAV can borrow the resources from other UAVs to perform some complicated tasks. The traditional distributed computing schemes allocate non-overlapping tasks to different computing nodes. And the disadvantage of such computing techniques is they are sensitive to system noises. And later I will use an example to illustrate this idea. The coding techniques have been widely used to improve the robustness of communications and storage and cache systems. And recently, it also has attracted a lot of attention from the distributed computing community. So since 2016, the coded distributed computing was first developed, and now is a very hot topic. And the key idea of this technique to resolve the struggle issue is that it introduces redundancy into the computation through erasure codes, so that these techniques can improve the resilience of the computing system to failures and achieve higher efficiency. So now let me use a small example to illustrate the key idea of these two types of distributed computing techniques. So let's consider a matrix multiplication problem. Suppose we wanted to multiply a pre-stored matrix A with an input matrix X. And in the traditional distributed computing systems, the pre-stored matrix A is decomposed into two submatrix, say A1 and A2, which are stored in two worker nodes. And upon the receipt of an input X, the master node would, in order to compute A times X, the master node first transmit this input matrix X to both worker nodes, and then each worker node computes AI times X, and then returns the result back to the master node. The master node can recover the final result by concatenating the results received from the worker nodes. So as you can see here, by concatenating A1 times X and A2 times X, we can recover A times X, because A1 and A2 are two submatrix of A. And if, as we consider the scenario, say if one of the worker node fails or is slow in computing, so then the master node, as the master node needed to wait for results from both worker nodes to arrive before it can recover the final result, right? If one of the node fails, it will fail to compute this computing task, right? And if one of the node is slow in computing, then the master node will also take a lot of time to recover the final result, because it needs to wait for both results to arrive. And now let's see how the coded distributed computing can resolve this issue. So in the coded computing, distributed computing system, we introduce redundancies. For example, we introduce another worker node that stores matrix A1 plus A2. So as now, this additional worker node will compute A1 plus A2 times X. And the other two worker nodes perform the same tasks. As we can see that the master node will be able to recover the final result once it receives results from any two worker nodes. For example, if worker node 2 fails, then the master node can still recover the final result A times X by concatenating by A1 times X and A1 plus A2 times X, because we can decode A2 times X by subtracting A1 plus A2 times X with A1 times X. And then with A2 times X, and then we can combine it with A1 times X to get A times X. Right. So in this way, this coded distributed computing systems improves the computing efficiency and is resilient to failures. However, existing coded distributed computing schemes still have limitations. In particular, we know that each worker nodes in the existing coded schemes needs to wait to send back the result until the whole task is completed, which may incur significant computation latency. And the master node won't output the final result until it receives sufficient results. So for UAV applications that require timely decisions, such schemes may not be suitable. And we need a scheme that is more efficient and can give output results more quickly. So to address this limitation, we developed a new coded distributed computing scheme. And the key idea is to allow partial results to be returned, which can be used to generate approximate solutions. So still, let's consider the matrix multiplication problem, say A times X. And the dimension of A is R times M. And A is a pre-stored matrix. And to perform this idea, we first encode the pre-stored matrix A with R rows to a larger matrix, say A hat, which has, say, Q rows, where Q is larger than R. So this step introduces redundancy into the computation. And the equation to compute this A hat is given by this, where H is the encoding matrix, which has any R rows being four rank. And the next step is to decompose the matrix A hat, sorry, this is type here. This should be A hat into N submatrices, where these submatrices are denoted as A1, A2, and so on, where N is the total number of worker nodes. So this figure illustrates the idea, right? We, upon receiving an input, the master node would broadcast this X to all the worker nodes, where the submatrices are stored in these UAVs. And upon now, this procedure is still same as the existing coded distributed computing scheme. And our scheme is to let each worker node I further decompose the submatrix AI hat into PI submatrices, with each submatrix has BI rows, where these submatrices are called batches. So PI is the number of batches, and PI is an important parameter that we need to configure in the algorithm that we will introduce later. So let's just keep this in mind. And then upon receiving the input matrix X, each worker node multiplies each batch with X and then returns the result back to the master node. And once receiving at least R rows of results, then the master node can recover the final result by using this equation. This scheme is called batch processing-based coded computation, or BPCC for short. Okay, so now we have introduced a new coded computation scheme. And next, we further explored approaches to optimize the performance of BPCC by exploring optimal load allocation. First, we consider a simple static network where UAVs are assumed to hover in the air and are static. So the distance between two UAVs is constant over time. And this is the problem formulation. Say, given PI, where PI is the number of batches for worker node I, we wanted to determine the optimal load allocation, where this LI is the load numbers. As you see here, LI is the number of rows for submatrix AI for worker node I. So this LI indicates the worker load assigned to worker node I. Larger LI indicates higher worker node. And we wanted to minimize the expected task completion time T. And this is a mathematical formulation. To describe the behavior of the computing time, we define a variable called TKI, which is to be the execution time of worker node I to compute K batches. And obviously, this TKI should be a random variable, follow certain distribution. And here we assume this time follows a shifted exponential distribution with a cumulative density function given as below. And this assumption is commonly, this computing model is commonly used in existing studies. To solve this problem, as you can see here, this is a nonlinear optimization problem. So directly solving this problem is very challenging. So instead, we propose a two-step alternative formulation. In particular, the first step is to maximize the amount of results accumulated at the master node by a feasible time T. And solving these problems, so this ST is the number of rows of results received by the master node by time T. So we want to maximize this expected amount of results received by the master node by a certain time T. And this gives us the optimal load numbers, which is a function of time T, where this lambda I is a positive solution to the following equation. And then the second step is to minimize this time T so that the probability that the amount of results received by the master node are sufficient to recover the final result. The probability is sufficiently large, right? The probability so that the probability of the master node receiving sufficient results is sufficiently large. And the solving this problem gives us this very simple mathematical equation. The optimal load numbers can be easily calculated using this equation, where R is the number of rows that is required to recover the final result. And S is equal to this equation here. So you can see this approach gives a closed form mathematical equation that allows us to easily and quickly get the load numbers, the optimal load numbers. And we prove that the solution to this alternative problem is asymptotically optimal. And now let's look at some simulation and experimental studies. Let's consider 4 scenarios with different values of R and N, where R is the task size and N is the total number of worker nodes. And we compare our method BPCC with 3 benchmark methods, where uncoded refers to a uniform uncoded scheme that equally divided the computation loads for different worker nodes. And the load balanced scheme is an uncoded scheme that would divide the worker loads based on the computing capability of the worker nodes, so that nodes with higher computing capability would get higher workload. And HCMM is a state-of-art coded computation scheme. And we can see here our approach achieves the highest efficiency in all the scenarios. And the right picture shows that shows the amount of results received by the master node over time in scenario 2. As we can see here, compared with the benchmark approaches, our BPCC method in our BPCC method, the master node is able to receive result at the very beginning, and it consistently receives the results over time. And at this point of time, right, is the time when the master node receives sufficient result to recover the final result, and also indicates the time that the task is completed. And for the other three methods, you can see that there is a large time slot at the very beginning that the master node does not receive any result. And we also conducted a lot of experiments on Amazon EC2. And here are some of the results. In the first experiment, we randomly pick 20% of the worker nodes as stragglers, which delay in returning the computing results. And the results still show that our method performs the best in all these scenarios. And this yellow block here indicates the time for decoding. And the right picture shows the amount of results accumulated received by the master node. And in the second experiment, we randomly fill 20% of the worker nodes. So we directly fill some of the worker nodes so that these worker nodes do not return any result. So because of these failed nodes, the computation task may fail. So as you can see here, for uncoded schemes, right? This one shows the success rate. You can see that the both uncoded schemes fail to complete the task because they do not introduce any redundancy into the computation. And the master node requires the results from all worker nodes to recover the final result, so that if any of the worker nodes fail, the whole computation task will fail. You see, compared with the coded scheme, the existing coded scheme, our method has achieves a higher success rate and also higher efficiency. And in the third experiment, we vary the percentage of stragglers with finite delay from 0% to 60%. So 0% indicate there are no stragglers in the system. So all the worker nodes performs well. And in this case, you can see that when there's no stragglers, the uncoded schemes performs better than the coded scheme. This is expected because uncoded scheme does not introduce any redundancy, so does not have any overhead, right? So when there's no stragglers, uncoded scheme performs better. But when stragglers exist in the system, the coded scheme perform much better than the uncoded schemes. And when the number of stragglers increases, the performance of all approaches degrade. But the BPCC still performs better than the other approaches. And in the fourth experiment, we vary the percentage of failed nodes, also from 0% to 60%. And as we expected, when there's no nodes fail, all the schemes can successfully complete the task, right? And the efficiency of the uncoded scheme are better. But when there are nodes that fail, then the coded scheme outperform the uncoded scheme. And our method achieves better performance. In the last experiment, we varied the number of batches to study the impact of batches on the performance of the approach. So we also did a lot of theoretical studies to analyze the impact, but I didn't put it here. So just let's see this graph to get a feeling about the impact of the number of batches PI. So to do this experiment, we let PI of each worker node to be the same, say P, and then increase the value of P. And as we can see that with increasing as P increases, the execution time decreases. So which means the efficiency improves. Okay, based on this study, we further explored the load allocation for a more realistic systems, mobile systems where UAVs can move randomly in the air. And in this study, we formulated the problem as follows. We assume that the master node receives a sequence of matrix multiplication tasks, where K is the total number of tasks. And given the values for the parameter PI, where PI is the number of batches, we want to determine the optimal load allocation for each worker node I and task J, so that the total expected task completion time given in the following equation is minimized. And to address this nonlinear optimization problem, we propose a multi-agent reinforcement learning-based formulation. And in this formulation, we regard each worker node as an agent that learns to achieve the optimization goal by interacting with the environment. The state of each agent at time t is given here, which includes the distance of agent I to the master node, the distance of other agents to the master nodes, the velocity of agent I, the velocity of other nodes, and the velocity of the master node. So upon receiving a new task J, each agent I decides the computational load it will execute for this task. Note here, in this formulation, each agent makes decision in a decentralized format. This differs from previous or existing distributed computing frameworks that determines the load allocation in a centralized format. So this decentralized decision-making alleviates the computing load at the master node. And the action of agent I taken at time tj, where tj is the time when the agent I, when the new task j arrives at agent I. And the action taken by agent I is defined as the load number. And this is the reward function, which aims to minimize the computation time and also would penalize the cases when the load numbers violate the constraint. So we have a constraint here. In order to complete the task, the total, the summation of the load numbers should be larger than or equal to P. And to solve this problem, we use a state-of-art multi-agent reinforcement learning algorithm called MAD-DPG, multi-agent deterministic policy gradient. And we used it to learn the policy. And we also applied the batch processing procedure we introduced in the previous slide to further improve the computational efficiency. In particular, we let each node compute each task in batches. So the key features of this approach is that it can adapt to time-varying communication changes caused by node mobility. Right? So this is actually a very important feature that we need to achieve in order to achieve networked airborne computing, because in network airborne computing, UAV are moving in the airspace, right? And the communication distance between each other would change over time. So we need a strategy that can, a distributed computing strategy that can adapt to these communication changes. And also it addresses node heterogeneity. So UAVs can have different computing capability and so on. And it is applicable for any systems without having to know their communication or computing characteristics. So with this reinforcement learning schemes, we do not require the knowledge of the communication or communicating or computing characteristics. So we do not need such knowledge. But in the techniques we introduced before for the static network, we actually assume certain computing models. So we assume the computing time follows a certain distribution. But here we do not require that. And this approach also achieves high computation efficiency, and the decentralized load allocation can relieve the computation burden at the master node. So now let's look at some simulation studies. So in the environment, we assume the UAV communicate with each other through direction antenna. And these are the model that describes the communication behavior or computing behavior of the UAV. And we assume the time follows a exponential distribution. So we know that this is just to generate the environment data, but to perform our algorithm, to make decisions, these models, we do not need to know that. And in the first experiment, we do not introduce any stragglers, and we compare our method with the other existing coded distributed solutions. So note that the existing uncoded or coded distributed computing schemes assume static networks. So they do not take a node mobility, which will change the network topology or communication quality. They do not take this into the consideration. Right? So you see here, our approach, which addresses node mobility and these issues, performs better than the other benchmark approaches. Even it works better than the uncoded scheme, even when no stragglers are present. And this graph shows the impact of the batch size on the performance. And in the second experiment, we randomly pick one UAV as the straggler. So as we see here, our method outperforms the other three methods significantly. So now I have introduced some of our recent efforts to enable network airborne computing. Next, let me briefly introduce some applications that we explored along this direction. So first, we explored the object detection, which is a very important application, a function that is important function that is needed to enable some UAV applications such as image processing, object tracking, and so on, search and rescue, and so on. Right? And we wanted to achieve real-time object detection on JSON TX2. And the results show that our network airborne computing platform can enable real-time object detection even with virtualization. And we also explored the usage of coded schemes to facilitate multi-agent reinforced learning based control. So we explored the use of coding scheme to improve the training efficiency for multi-agent reinforcement learning algorithms. And these show some multi-agent reinforcement learning control applications such as coordination, navigation, predictive array, and so on. And the results show the benefits of the coding schemes in helping speeding up the training for these algorithms, especially when we wanted to control some large scale multi-agent systems, and have some systems that may fail, right? And such coding schemes will help such scenarios. So besides of these many efforts we have made so far, there are many other challenges that we need to counter in order to fully realize network airborne computing, right? Some key technical challenges include high 3D mobility. UAVs operate in a complex 3D world with high mobility. And such high mobility can cause frequent network topology changes, link failures, data losses, and task interruptions. Our previous methods addresses these issues in certain extent, but we assume the UAV are having, we assume the UAV operate at the same altitude. So in a 3D airspace, and we assume the UAV has very simple dynamics, which is not quite realistic. And another challenge is high dimensional uncertainty. So because the UAV operate in the resource constrained national airspace system, which consists of a variety of uncertainties, and these uncertainties can modulate the dynamics of the UAV, and it can also disturb the communication among the UAV. So the desired distributed computing techniques should be robust to these high dimensional uncertainties, and this requires efficient uncertainty evaluation methods. And also UAVs have strict safety requirements, which require the UAV to respond in a timely manner and satisfy mechanical and aerodynamical constraints. So these key challenges actually make the network airborne computing differ from traditional mobile computing system like mobile edge computing, mobile fog computing, and so on, which are operate on the ground, right? And these challenges are phenomenon for network airborne computing. And existing designs for traditional mobile computing systems, which does not, which consider mobility, uncertainty, and networking as constraints, may not work. And our idea is to proactively exploit the mobility, uncertainty, and networking to enable high performance designs. And this is our future work. Finally, I would like to thank my collaborators, my PhD student Baoqian Wang, and Dr. Yan Wan, Dr. Shenli Fu, Dr. Keji Lu, and Dr. Nikolai Atanosov. And I also wanted to thank the National Science Foundation and SDSU for the financial support. Before I end my talk, I would like to briefly introduce my SMILE lab, which does not limit, the research areas we do does not limit to networked airborne computing. We aim to explore fundamental theories and innovative algorithms to improve the efficiency, resilience, scalability, and safety of dynamical systems and networks. And we work on a lot of research areas besides of system control, modeling, decision-making, computing. We also work on uncertainty quantification, machine learning, and artificial intelligence, and work on a variety of applications such as like ground robot systems, cyber physical systems, and air traffic flow management. Thank you. This is all for my presentation, and I would be very happy to answer any questions you have.
Don't be shy.
Yeah.
Any questions from the audience? Well, thank you very much for your very educational and well delivered talk. So I actually learned quite a bit. And
Thank you.
Thank you everybody for attending the colloquium, and have a nice weekend.
Have a nice weekend.
Bye-bye.
Actually,
Bye.
I have one question.
Okay, go ahead,
Yeah.
Lena.
Good. What is the, I have to go back to one slide, the high, let me look at this slide here. How to pick. What is the, was it high uncertainty, high dimensional uncertainty? What does that mean?
High dimensional uncertainty means it has a lot of different types of uncertainties. Right. For example, uncertainties can exist indirectly in the environment, like wind disturbances, right? And can also exist in like communication links, system inside of the system. So there is different uncertainties, like you can consider as you can characterize as random variables, right? So you can imagine there are many random variables that would modulate the dynamics of the system. So when we control the system, we needed to take these uncertain variables into the consideration, because it would impact the output of the system. If you consider the system as a blackboard, right? These uncertain variables would modulate the system dynamics and would modulate the output. And then you wanted to design some control solutions that can be robust to these uncertain random variables.
Okay. Thank you.
You're welcome.
Anybody else? Okay, well, bye-bye everybody, and thank you.
Bye.
That's it.